Hello chemistry students, in this video I'm going to go over enthalpy, entropy, and Gibbs free energy as we start learning about thermochemistry. Alright, so in chemistry there are a lot of energy transformations. So in thermochemistry we're going to study energy changes that occur during chemical reactions and changes in state. Something for you to realize is that potential energy is stored in chemical bonds, and then during chemical reactions bonds are broken and new bonds are formed, and that results in energy being transferred, sometimes absorbed, usually released. Alright, so heat is energy that gets transferred from one object to another. It's not an entity of itself, but it's measured as exchanges take place. Alright, so what is heat? Heat is energy that's transferred or flows from hot substances to cold substances, represented by the variable lowercase q. Alright, as you add heat, that can cause physical changes such as increase in temperature, melting, vaporization, boiling, or evaporating, depending on what temperature you're at. And then removing heat can cause decrease in temperature, freezing or solidifying or crystallizing. Those are all describing the phase change from liquid to solid, or condensation. That's the change from gas to liquid. Alright, heat transfer is going to continue until there's no temperature difference between whatever objects are involved. So here's a little compare and contrast for temperature and heat. So heat is a better way of describing total kinetic energy, or at least a transfer of kinetic energy, while temperature is just a measure of the average kinetic energy of the molecules in whatever substance. So total versus average. So this is a quantity and this is an average. Okay, heat has the same energy unit as, has the same unit as energy, which is joules, while temperature has the units of Celsius or Kelvin. And recall, you can convert between Celsius and Kelvin using the Kelvin equals degrees Celsius plus 273 equation. Okay, you can't measure heat directly, but you can measure temperature directly. Alright, so heat is transferred from a warmer area to a cooler area until equilibrium is released. So here we have a picture of some ice and some water, and the heat is going to travel from the water into the ice until you reach an equilibrium temperature. Now, eventually all the ice is going to melt here because the system, which we're including the water and the ice, isn't actually closed off from the room. So heat from the room enters in and goes into the water and then goes into the ice. So it's still a transfer from hot to cold. And you may have noticed that if you have a good insulator as your cup, like maybe a styrofoam cup instead of a glass or a paper or plastic cup, that the styrofoam is better at isolating the system, your drink, and the ice from the surroundings, so you don't have the heat from the surroundings go in and melt the ice quite as quickly. Alright, so let's talk about the law of conservation of energy as well as definition of system and surroundings. So the system would be whatever object or objects you are interested in, while the surroundings is everything outside of it. And the law of conservation of energy says that energy is not going to be created or destroyed, but it can be transferred and change form. Sometimes the energy might be transferred from the surroundings to your system or vice versa. And if you wanted to conduct your experiment in isolation, at least in terms of heat, then you would need to insulate your system very well to prevent transfer of heat between the surroundings and the system. Alright, so let's talk about changes in energy and changes in disorder of our particles here. So, first we'll talk about enthalpy. So The enthalpy is a measure of the heat content of a substance. Most chemical reactions that occur naturally are going to be exothermic, and we'll find out why a little bit later when we talk about Gibbs free energy. So exothermic because they go from a state of higher energy to a state of lower energy, kind of like a ball naturally falls from the higher gravitational potential energy to the area of lower gravitational potential energy. All right, entropy is very different than enthalpy, even though the words kind of sound the same and they start with the same letter. Okay, and just to go back and make sure I got this, variable for enthalpy is H, the variable for entropy is S. So entropy is all about disorder or randomness of the system, and in natural circumstances usually entropy is going to increase, kind of like enthalpy. Most natural reactions are going to increase in disorder or increase in entropy. So just a thought for you here, if you put 3 different layers of marbles in a container, or 3 different colors of sand, like if you do a sand ceremony at a wedding, and then you shake it up, like they're never going back to the layers. Disorder is going to increase, so therefore entropy is going to increase. Alright, so here's a few more examples. The molecules in liquid water are more disordered, have more degrees of freedom of motion, while the molecules in ice are in a crystalline arrangement. When solutes dissolve in a solvent, the entropy also increases. For example, we'll see this paint dissolving in the water here, and you can imagine that if you leave this for a while, it'll eventually mix up and get into probably kind of a brown color or something. They won't stay separated like this. They'll mix up until you reach the maximum disorder. Alright, so here's a compare and contrast of enthalpy and entropy. So the symbol H for enthalpy, S for entropy. Enthalpy measures heat transfer. Entropy measures the degree of randomness. Some terms for you: chemical reactions where the change in enthalpy is positive. That means that chemical reaction is absorbing energy, while delta H, a change in enthalpy that's negative or less than 0, that is exothermic. So that means that energy or heat is being released by that reaction. Something that's kind of odd about this is that endothermic reactions, if you felt of the reaction as it was taking place, the reaction mixture would feel cold to you because it's absorbing heat from the surroundings, while the exothermic reactions, those are the ones that get hot and produce energy, because the negative sign means that they're releasing heat to the surroundings. Alright, let's see. So delta S, the entropy change, if it's positive or greater than 0, then that means that entropy is increasing, or because disorder or randomness is increasing. And if delta S is less than 0, then the entropy, the disorder, the randomness is decreasing. Okay. So things that have a high degree of order, crystalline solids, things near absolute 0, so that would be a very low value for entropy. If you're very orderly, not disordered, then you have low entropy. Liquids have more entropy than gases have the most. Ordered that here: solid is less than liquid is less than gas for entropy. Alright, so here's an example with the puzzle. Simply stated that if you have a jigsaw puzzle, when it's all put together, then there's very low disorder. When it's broken apart in all the pieces, it is much more disordered. Alright, so let's take a look at a chemical equation here. kind of like the puzzle, the side with the most pieces, especially the most pieces in gas state, is probably the side with the most entropy. So you notice here for the photosynthesis reaction that there are 12 pieces on the left side and there are only 7 pieces on the right side. So that means that entropy decreases in this reaction. Alright, some other examples here. So melting ice, that increases disorder, so that's a positive entropy change, while the opposite, water freezing, is a negative entropy change. And we're not going to go through right now and do the entropy calculations, but you could do these, and I'll buzz through all of these. So we're not doing those right now. Okay, now let's get and talk about Gibbs free energy. Alright, so Gibbs free energy is a way to measure, you could say, chemical potential, basically trying to figure out, will the reaction proceed as written, or is the reaction spontaneous? So we're trying to predict the spontaneity of chemical reactions. Why do some things move forward? Why do some things not? Alright, so spontaneity. If a reaction is spontaneous, it will proceed without any outside interaction or intervention. Just put the reactants together at the whatever temperature and they'll react. Might not be fast, could be slow, could be fast, but the reaction will move forward. Reactions are going to move toward equilibrium, and we'll go through and show this Gibbs free energy calculation where we can point out that that would be the point at which delta H and the temperature times the delta S are equal to each other in magnitude or size, and that would be the point where delta G would be exactly 0 and everything would be in equilibrium. Alright, so we'll use an equation to figure that out, and it is this equation. So the Gibbs free energy equals the enthalpy change minus the temperature times the entropy change of a particular reaction. And this minus sign here can make things a little bit difficult, but we'll try and get through it. So, alright, so when you do this calculation and it returns a negative value, the reaction is spontaneous, a negative value for delta G. If the delta G value is positive, then the reaction is not spontaneous. And if you get 0, then you're at equilibrium and the reaction's not going to proceed in any direction. Alright, so let's look at a sample problem here. Basically, you would be given the delta H and the delta S for these reactions. Maybe you'd have to convert, like the joules to kilojoules or kilojoules to joules so you can compare the units. Basically, you plug this in, the delta H minus the temperature in kelvins times the delta S, make sure the energy units match, and then you get a number. That's a negative number, so the reaction is spontaneous. Alright, so just a review of the equations here, and let's go through and make some predictions here. So, if you have a negative delta H and a positive delta S, then the put in a negative here, put in a positive for the delta S, the temperature will be a positive, so negative times a negative, negative times a positive gives you negative. You already had a negative here, so there's no way you get anything other than a negative value for delta G. That means your reaction, in this case, with a negative delta H, negative enthalpy change, positive entropy change, it's always spontaneous. With this combination, positive and negative, there's no way to get anything but a positive. Say positive here, negative delta S, so negative times a negative gives you positive. Positive values added together, you're always going to get a positive. So that's always not or non-spontaneous. And then these two, you have to calculate them because one value will be negative, one will be positive, and you have to see what happens. Thanks for watching.